Well, hello, everybody. My name is Reed Miner. I am now retired for about the last year or so, but before that, I worked for an organization called NCASI. NCASI is an environmental research organization funded largely by the North American forest products industry. And the way I come to this issue goes back to the late 1990s in the lead up to the Kyoto Protocol meetings. We started getting questions from a lot of companies asking what this climate change and carbon issue meant to them. And as a result, I became a carbon accountant for all intents and purposes. And in the subsequent 20 plus years, it led to a series of collaborations and interactions with groups as varied as the Environmental Defense Fund, WRI, and the World Bank and IPCC and others. So what you're going to see today is essentially a distillation of that 20 years of carbon experience as it relates to the question of carbon neutrality. And then we'll speak a little bit about how that connects to life cycle assessment and substitution effects. Now, as you can imagine, just thinking about the term, carbon neutrality means that something is zero. We've done some kind of calculation that implies zero net emissions of biogenic carbon from a product system. Unfortunately, as you will see here, there is no agreement not only on the definition of carbon neutrality, or even on how you do the calculations. Indeed, I have tried my best over the last 20 years to avoid the term entirely, because ultimately what we're talking about here is the net emissions or flux of biogenic carbon from a product system. Also important to understand that carbon neutrality is different than substitution effects. All we're looking at when we're talking about carbon neutrality is biogenic emissions. Now we're going to look at 4 different approaches to doing these calculations. I will not read through these and understand that these are basically 4 basic approaches, but you can imagine myriad variations thereon. We're going to look at all of these using this approach. We will have a system consisting of a forest, product manufacturing, product use, and end of life in the rest of the value chain. We have a system boundary, the dashed line here, and we get removals of carbon from the atmosphere into our system in the forest, and we have emissions from our system back into the atmosphere through the rest of the value chain. And the question that we're going to try to answer is, what is the balance? What's the net flow of biogenic carbon from our system given all of these fluxes? Let's start with approach 1. We're going to start our accounting back when our tree starts to grow. And as that tree grows, it removes carbon from the atmosphere. Then we harvest that tree, and that carbon goes into product manufacturing, product use, end of life, and we see that there are emissions of biogenic carbon through these various life stages that offset the emissions, the removals that we had back in the forest. Note here that if the carbon in the tree, which represents all of these removals from the atmosphere, if that carbon is equal to all of these fluxes back to the atmosphere, then the net flow across our system boundary is 0. Some people might call that carbon neutral. Indeed, this is the approach that was used almost universally, I'd say, until about 10 years ago in life cycle assessment. And one reason is that it is so perfectly aligned with life cycle thinking. Think of the carbon here. The individual carbon atoms that we're moving back here in the life cycle are the very same carbon atoms that we end up emitting back to the atmosphere later on. So we've very nicely defined system boundaries and done our carbon counting in a way that is consistent with life cycle thinking. One downside, though, is that this approach basically considers all trees the same. If this tree was harvested and resulted in deforestation, you would likely get the same picture as one that was harvested from a plantation that was sustainably managed on an ongoing basis. Now, of course, you can prevent that from happening by putting constraints on this approach. You could say that you can only use this approach if you're practicing sustainable forest management over time and other things. But just as it stands, without any constraints, one of the downsides is that you don't detect deforestation. Now let's go to approach 2. In this case, instead of starting the accounting when the tree starts to grow, we start the accounting when we harvest the tree. So the tree is harvested, it goes into the value chain, we have emissions from the value chain. And in approach 2, the removals of carbon from the atmosphere that we get are in a new tree that we planted to replace the harvested tree. So we get carbon coming out of the atmosphere and removals from accomplished within our system boundaries. And we look at the balance between the arrows going out of our system and the arrows coming in. Note that if all of these arrows are the same size, if the flows into our new tree are the same as the flows going back into the atmosphere from the value chain, we have net zero emissions or neutrality. Things are a little more complicated than that though, because we really don't know what's going to happen in the future when we plant that tree. How big is it going to grow? How fast? What are the factors that might impact its growth, disturbances over time? So we've introduced some uncertainty when we use approach 2 because we're trying to project future conditions. Also note that this new tree that we're growing, that we have in our system boundaries, isn't really connected to the carbon in our product. It's kind of an artificial system expansion. So it's not quite as pure from a life cycle standpoint as approach 1 was. On the other hand, note that we have directly captured deforestation in this approach. Unless we grow a new tree to offset the one we harvested, we don't have any removals of carbon from the atmosphere accomplished by our system. So we definitely capture deforestation with approach 2. Now let's look at an approach that's a little bit different from these, approach 3. Here, instead of looking at a single tree over time, what we look at is the entire supply area supplying our facility or our industry. Let's look at a simple case just for thinking about it. Let's think about a plantation that was established on a sustainable basis to supply wood on an ongoing basis to a facility. So there are trees of all different ages in this plantation, and we harvest some of them every year to feed our facility while the others grow. In this approach, what we do is take a period of time, often it's 1 year, January 1st to December 31st, and we consider all of the carbon that goes into our forest over that 1 year period. We then track the amount we remove in 1 year's harvest, which is only part of what was in our forest, follow it through the value chain, and follow the emissions that go back into the atmosphere. And we do that to some point in the future where we are comfortable in stopping our carbon accounting, perhaps because all of this product carbon has returned to the atmosphere. Note in this case that if the carbon being removed by the forest over a 1 year period is equal to the carbon that we removed in 1 year's harvest and returned to the atmosphere, then the yellow lines coming into the system are the same as the yellow lines going out of the system. Net emissions are 0. We have a neutral system. Also note, quite conveniently, that another way to test this is to look just at the carbon stocks in our supply area. If the amount of carbon we remove every year in a harvest is offset by the amount that's removed by growing trees, then the amount of carbon in the forest, the carbon stocks remain stable. So we can quite simply look at what is happening in the forest, the carbon stocks, and make a judgment as to whether or not we have net zero emissions from our system. In other words, we are neutral. Also note that if we have deforestation, in other words, if we're harvesting more carbon from the forest than is being taken out of the atmosphere by the forest, our carbon stocks will go down. So we will pick it up in this calculation. On the other hand, this approach faces us with some interesting questions. Most particularly, what is the supply area? How are we going to define that? We could talk about a simple approach, a single plantation supplying a single operation, but we may be interested in looking at other definitions of supply area and landscape that are larger spatially. We may need to think about practical issues over what regions do we have data, how can we isolate with data the effects we're looking for, what are some of the other factors that influence what's happening in that supply area, other disturbances, market forces, urbanization. So you're faced with some interesting and important questions when you use this approach. Nonetheless, as we'll see later, what's nice about this is it's aligned with wood procurement practices and lets us take a larger scale view of what is happening in the forest and consider some factors that we might not otherwise be able to consider. And we'll return to that. Now in approach 4, we take one of the other approaches that we've already talked about and we overlay something onto it. Here we're going to start with approach 2, which you remember we start the timing at harvest and then we grow a new tree to replace that harvested tree. In approach 4, what we do is we add a counterfactual tree. In other words, the counterfactual tree is the tree that would have existed if we hadn't harvested it. So the counterfactual tree continues to grow over time. As it continues to grow, it continues to remove carbon from the atmosphere. And then what we do is we say, well, we are going to consider that foregone sequestration as an emission from our system. So it's going to make things look worse than they otherwise would have because we've included this counterfactual. Note that not only now do we have the additional assumptions about what the new tree looked like, we now have to make some more assumptions about what would have happened to the harvested tree if we hadn't harvested it over time. And you get into the same kind of issues of growth rates, the time period you're looking at, how disturbances might affect the area and things like this. In addition, we've clearly included a tree here that is not part of our the carbon that was in our system because the carbon in our system was harvested and returned to the atmosphere here. Here we're talking about additional carbon that is coming out of the atmosphere if we hadn't harvested the tree. So it's not nearly as clean from a life cycle standpoint. Obviously requires a lot more assumptions. So the answer to the question of, is our carbon neutral? The answer, as always, of course, is it depends. We saw a traditional LCA approach, approach 1. In most cases, you'll find biogenic carbon being, quote, neutral in this case, but we saw that unless you put constraints on it, you can miss instances of deforestation. We looked at another approach, approach 3, that looked across a landscape or supply area. This is how wood is actually grown and procured. So it's nice from that standpoint. It aligns nicely with a lot of the data that people have. It's also nice in that we can make a judgment as to whether whether emissions are net zero or better or worse just by looking at carbon stocks over our supply area. It captures deforestation because within the supply area, although our ability to detect that will depend a lot on how we define the supply area, the scale and other things that we use to define it. In addition, if we use a very broad definition of supply area, a very large one, it may be difficult to isolate the carbon uptake that's due specifically to our product. Now that may or may not be important, and it may or may not be as important as some of the other factors we're about to talk about. The other approaches we talked about can be useful in a number of circumstances. I don't want to dismiss them at all, but they clearly involve some uncertainty and assumptions that can be very important to the results that you get. So you need to use them with that understanding. And especially ones that involve counterfactuals, you need to be wary of. Now, everything we've talked about so far has looked only at biophysical factors. That is essentially a mass balance of carbon. And what that means is we've assumed that if demand increases, the only thing a landowner is going to do in response to that increased demand is increase their harvesting. And there's a perception in some cases that that is equivalent to deforestation. But in fact, the empirical evidence and the modeling that has been done is the exact opposite. What happens to forested area when demand for wood increases is you get more forested area. And in fact, you find you get more productive forest management. And it's kind of intuitive. If you're a landowner and you are faced with the decision of how to use your land, if you have a market for wood, it gives you an incentive to leave that land in forest instead of perhaps converting it to ag land or some other purpose. I won't read these quotes on the left. You may want to look at these references if you have concerns about this finding, but I can tell you essentially every study I've ever seen that goes beyond biophysical factors and includes economic factors, market factors, and landowner responses finds this. You get more forested area with increased demand where you're in an area where there is sustainable forest management practiced, like the United States. Now, the carbon responses are a bit more tricky, but they're important. In general, when you're talking about an increased demand for sustainably produced wood, what you find in the short term is a reduction in carbon stocks as harvesting increases. But then over time, as landowners respond to that increased demand, you find that stocks recover. And in fact, you may find cases where the stocks even go higher than they would have as a result of that increased demand. But it's very site specific. And at the risk of making your head explode, I'd like you to walk through these two figures with me. This is an example from a USDA study of the Southeast US. And they were interested in looking at what would happen to forest carbon and forest wood prices if there was a new demand for wood pellets in the Southeast. There's a whole bunch of information in this report. I pulled out two plots showing on the left what happens to a number of variables without that increased demand. On the right, what happens to those same variables with increased demand. First, let's look at the blue line. That's the price for small pine timber. We see without increased demand, it goes up and down a little bit, but stays pretty stable out to 2040. Look what happens though with increased demand. As you'd expect, the prices for small pine wood increase dramatically. Now, for our discussion here, that's not what we're interested in. We're interested in carbon. And that's essentially the dotted black line here. That's the inventory in the forest. Without increased demand, we find it's pretty stable from 2010 to 2040. With increased demand, we find indeed in 2025, we have less carbon in the forest than we would have had we not increased demand. But look out here in 2040. Due to the way landowners have responded, we actually have more carbon in the forest in 2040 with increased demand than we would have had that increased demand not occurred. Now, understand this is not what you get every time, but you'd be surprised how often you get it. And clearly there is some response, and that response is essentially always to offset some of this drain, some of this loss of carbon stocks that you will find if you use only biophysical modeling. So the message to me has always been, you ignore market forces and landowner responses at your peril. Now, just quickly a word about substitution effects. All I will say is that they are not the same as carbon neutrality. You can do all of these calculations and find that you have some biogenic carbon emissions from your product system. They are not zero, but that still doesn't mean that you're not going to get life cycle benefits, because in a life cycle study of substitution effects, you look much more broadly than just biogenic carbon. And with that, I will say thank you and look forward to the questions that we will get in the next webcast.